Because it was muted. The audio should be going through now. Yes, I should be able to say something, and you guys should be able to hear something. I'm doing the saying part. Yeah, that is. Worst come to worst, we can still do the thing where we stream on your. How do I fix that? Desktop audio, never mind. It should go through as well now. Properties. It's fine, no technical issues at all. You. Okay. Yeah. This is the text stream. Okay, say something. Alright, I think you say something.
Hold on, give me a second.
Yeah, no, it's going through now.
So you are certain it's going through now?
The audio mixer is picking up your voice.
Yeah, okay, it is going through, good. I've checked. Hello everyone, welcome to the first Academy stream. How are you all doing? Hi there. Right away, before we even begin, I could announce should we send the resources to kind of follow along as the stream is going on?
I suppose that is a very great idea.
All right, well then, here we go. The Academy. It has begun. The Academy is a project we've been working on for quite a while now. Mainly Remco with his team. That is Komi, Zaki, Adrian, who is here.
Hello.
There we go. And the Academy is going to be a series of courses on different topics, but we are starting with physics, and it's going to be a course about physics starting from the very, very, very basics. The idea is that even if you have absolutely no background in physics, you will still be able to follow along, and it will actually build up to something larger, something great, something grand. You actually get an extremely in-depth understanding of physics. But alas, as I mentioned, it's not really... Like, we have been working on it, but it's mainly Remco's project, so Remco is obviously going to be the teacher here. Hence why Remco is streaming right now. It's honestly pretty unsettling to have someone else streaming on my main channel, but... Well, we had to pick the most popular channel, so... I hope you...
That would not be mine.
I hope Remco won't demonetize me, because... Well, actually, honestly, it will take... I hope that you want to get this channel banned, mainly. If you manage not to do that, then... otherwise, the foundation might struggle.
I do not have bannable items on my PC, don't worry about it.
Yes, you certainly do not.
Everything is fair and square.
Okay. So, it seems like there is no echo. Komi was saying that there is an echo, but Flash says that there is no echo, so...
There should not be a way for there to be echo.
There shouldn't be an echo, and given how Komi is the only one saying it, I would guess it's not a problem. And given how it is the time, I suppose you may begin. Right?
Already? Already?
I mean, if you want, we can stall a little bit longer. Will it be
fine. Let's go.
Will it be a video or say type or archive of this live stream? It's going to be a lot of things. It's going to be live streams, videos, documents, posters, exercise sheets, tests, quizzes, interactables.
Just everything.
Everything but the kitchen sink. And then we're gonna make a kitchen sink out of it. All right, but with that in mind, I suppose it is time for us, Adrian, to retreat into the shadows and give Remco the stage.
Yeah.
Why,
So,
thank you.
Remco, what is physics?
Physics. Physics is the science of nature, everything around us. But that doesn't tell a lot because there is a lot around us. So perhaps we should take it a little bit simpler. Physics is a course at university. I'm not pleased with that definition either. Let's try again. Physics is the field to give a description of the things we see around us. Let's give an example of that. If I throw a tennis ball, do not ask why I'm throwing a tennis ball and not hitting it with a racket. Do you hit those things with a racket? I don't play tennis. Anyways, if you throw a tennis ball, you wish to describe the motion of this ball. You want to be able to see how it's moving or describe how it's moving, but also predict where it's going to end up. That is the core of physics. We are trying to not only describe our universe, we are trying to explain the things that we cannot explain or haven't explained before, but we're also going to predict new things. We want to be able to tell when something is going to happen. A very simple example of the severity of this is if an asteroid is moving towards Earth, well, we would like to know if it's actually going to hit it or if it's going to pass by. Like very important things that require the theories of physics to determine it. So in this new course, as already mentioned, in this new course we'll try to approach physics from a very fundamental level. So in particular, we will essentially not require any previous information. You should be able to follow this regardless of your skill level. I will go a little bit through preliminary content, but they are very, very basic and they should... I believe that everyone here should be able to like have an intuition for those concepts. It's just putting them down on paper what is usually the hard part. So, in particular, in this course, we have a couple of things. I have a new whiteboard, so I have to get used to this a little bit, but it's such a cool whiteboard, and you guys will see soon why. Is there actually dark mode? I should have probably checked this before. Anyways, the course slice of physics, of course, related to the slice of foundation physics. And in particular, we will be covering classical mechanics or the theory of classical mechanics. These are essentially the theories that, among other, but Newton wrote down, and also continuing on it, for example, Hamiltonian and Lagrangian. We will not do any modern physics yet. We will first try to lay the proper foundations of physics. And I would say classical mechanics is one of these foundations of physics. So for this course, we will have a couple of resources. And the first one is, of course, this stream itself, which I think that's slightly redundant. The second one is a set of lecture notes written by Adrian, Komi, Zaki, and me, which we form a team to make this course and make all these resources. Very special credits to all of them. They are amazing people, and I could not have done this. I would not be able to do this without them. Next, we have a lot of exercise sheets. We of course have normal exercises, which are basically indicators of whether you understood the context of it. But we will also do something that usually isn't done in classes, and we will go beyond these exercises. We will introduce a kind of like themes in exercises. So, for example, if you're very mathematically orientated, if you prefer mathematics, we'll have an exercise set that is like focusing on a mathematical side. Whereas if you are into mathematical physics, so more of a theoretical side, we'll have a very fundamental exercise set for you, or we have it planned. There is also there will be interactive exercises on the website. More on that in a second, and we will try to make a lot of variety in the exercises, because exercises on themselves are boring if you're not interested in them. But if there is something that overlaps with your interest, it's much more fun. So, with that regard as well, please give suggestions, and if you think something would be cool, just feel free to mention it. We are open for a very lot of things. Next thing, of course, there will be videos. In particularly, to answer a couple questions in chat, this live stream itself will be most likely reduced into a video without all the dead space. So there is always a way to watch this back. But we will also release additional videos. For example, on topics that are slightly adjacent, but we didn't have time to cover them in these lectures, or on entirely new topics that are in some way related. And very importantly, all these resources, they can be found on the library, or also the academy. I will write academy. And these, there should be a couple links in the chat that make it send where you can view them. Particularly, all the necessary resources are in the library, but in the academy we order them in a nice and presentable way, so you can go through them chronologically and learn step by step. So, enough with the boring basics. Let's get to physics. Let's begin. So, as I already mentioned in the introduction, physics tries to explain the universe. But the universe is a very, very, well, I would say overwhelming quantity. There's a lot of things happening, and we can't explain everything at the same time. And for that, in physics, we have introduced something called models. Essentially, models are approximations of the physics of everything that's happening around us, in such a way that it becomes very easy to describe it. So, for example, when we have the tennis ball that we are throwing for some reason, a model to describe this motion, well, the tennis ball is basically colliding with a lot of air particles. There's friction. There's friction from the air. There is a lot of stuff happening. It would be way too complicated to describe all of this. So instead, we could see, or, well, pretend that this doesn't exist. We can ignore air resistance and try to describe the physics with this. This would then be a model. It wouldn't be actual reality because, of course, in reality we have the air resistance, but it would be sufficient to, in most cases, it is sufficient to describe what's happening, because the air resistance might be very, well, negligible. There could barely be any air resistance, especially when you're talking about bullets or darts, for example. So, what we are trying to do is simplify the model, simplify the physics as much as possible, without, well, basically keeping all the important parts roughly set. Once again, very important, these models, or if they are big models, we also like to call them theories, they are still approximations. They are not reality. They try to describe reality. it's a very important key. It's not, we're not actually describing our universe. We are trying to explain a approximation of our universe. Okay, so now I suppose it might be a good moment to describe. Oh no! Oh, that's amazing. Okay, this whiteboard is cool. Now might be a good moment to describe some of the necessary context that we need, that we assume that we assume known. This is not going to be a lot, but it is necessary to discuss. So let's see. I'll try to make my handwriting readable. Actually, before I go to this, what I have made is an overview of today's lecture. There we go. And this is all we're going to talk about today. Prominently, we will start with these preliminaries, and this is going to be a discussion about numbers and how we can combine them. We're going to introduce variables, and with these variables, we are going to perform algebraic manipulation, as I coined it, but it's just doing some stuff on both sides of the equation so that we get new expressions, or solving for x, for example. We will also talk about functions and graphs and units. Only here the physics really enters. Everything else should be high school mathematics. Then we are going to consider a model, and I will mention more about that when we get there. So let's go. Numbers. In physics, we have a lot of numbers. Well, in mathematics, we also have a lot of numbers. But I guess the most common numbers are those used for counting. So, for example, 1, 2, 3, 4, etc. We could also count, or have no. Let's say we talk about, I don't want to say coins. Coins is too basic. Let's say we are counting carrots. Let's count carrots. So we could have 1, 2, or 3 carrots, but we could also have no carrots. And of course, this is represented by 0. With carrots, however, we could also owe a carrot. So that we have to give a carrot to our neighbor because he gave a carrot last year to us, and now we need to give it back to compensate. And this is a natural introduction for negative numbers. These are also very important. Minus, etc. These just keep going. But with a carrot, the nice thing what we can do is we can cut it in half. And then we have half a carrot. So we also have fractions that we need to consider. That's very nice. But our carrots have a circumference. And this circumference also introduces a new type of number that cannot be expressed in terms of a fraction. Irrational numbers. Or when combining them with the fractions, we get real numbers. I guess the main takeaway of this little number gap is that we just have a... Why is my Ctrl-C not working? That we have a line where we have a 0 somewhere. Wait, hold up, I have a tool for this. Don't worry, don't be afraid. Where is it? I can, don't worry. Number line. Yes, there we go. We have a number line, and on this number line, there are, we can just pick a point and we get it represents a number. That's the part of mathematics that we need. We just need numbers. All right, that completes the number part, but we can also combine different numbers. And one way of combining different numbers is addition. We can just add two numbers together. We can also subtract two numbers. We could multiply two numbers. So 2 times 2 equals 4. Please, I really don't want to make a mistake here. We could divide two numbers. 4 divided by 2 equals 2. Well, technically multiplication is a shorthand of addition, of like repeated addition. So 2 times 2, or actually 3 times 2 would be 2 plus 2 plus 2. And we can also define a repeated multiplication, which is done by exponents. So for example, if we have 2 to the power 3, this would mean 2 times 2 times 2. And this, of course, equals 4 times 2 is 8. We also have an inverse of this, and this is, of course, the roots. So, for example, the cubic root of 8, or the third root of 8, and this should be 2. We will write this in a slightly different form. We will write the roots as a fraction. So in particular, we would write. Oops. I don't think we might not encounter this today, but in general, if you see a exponent with a fraction in the exponent, this means that we are taking a root, and in this case, a third root. Okay, that's operations, which means we have completed our first. We have completed our first item. We are on a roll. So, numbers and operations, they should be very trivial. Let's talk about something a little less trivial now, variables. In particular, sometimes we want to make a statement or many statements at once about some number, but we don't want to give it a value yet. And this is where we introduce our famous x, the x in mathematics. So, as an example of why this would be useful, let's say that x is some integer, or rather like a natural number, so it's 1, 2, 3, or 4, or anything higher. Then we could make a statement of x plus 1 also being of this form. Why this seems very trivial? It is. For example, we could have x equals 3, then x plus 1 equals 3 plus 1 equals 4. This, of course, is of this form. So this makes sense. However, writing it like this, no, don't delete it. Writing it like this means that we are taking a lot of statements in one go. We are talking about x. We could be talking about x equals 1, x equals 2, x equals 3, etc., etc., etc. We don't have to write them all down. So it's basically not taking a value for x yet. Means that we have a lot of freedom in what we're doing. It could mean any value we specify which values it can take. But it is very useful to consider a variable like this. Another reason where this could be very useful is when we are talking about equations. So, for example, if we have the equation x plus 3 equals 8, and we want to solve this, then, we don't know what x is yet. So we represent a value that we don't know yet, also with x, and we wish to solve this equation. In this case, it's very simple. We just subtract minus 3 on both sides, and we obtain with x equals 5, which we have now specified our x. Don't delete it. Okay. that's variables done. We are speedrunning this. In particular, this brings us to algebraic manipulation, which I don't want to say too much about this, but the idea is if you have some equation, so let's say you have some equation like this, 5 equals b. With algebraic manipulation, this basically means that we are trying to isolate x, the same way we did this for the equation before. So we want to find an expression for x, and this just means that we need to follow some steps. So in this case, we first need to bring the 5 to the other side. We then need to divide by a to get the a to the other side. We then want to get rid of this square, so we take a square root on both sides, and we end up with an expression x equals something. This is a skill you need to know, and it's also a skill elaborated upon in the lecture notes. So if you have any struggles with that, go read the lecture notes on that. Then what is very important are functions, because a function is basically an object or a rule. You can think of it as a rule, and you give it some input. You give it the input x, and what you get is an output that we write as f of x, where f is the function. So basically, you are giving it a number, and you're getting back a number. For example, we could have the function f of x equals x. We could simply try this, for example, with x equals 2, then our f of x of 2 would give us back the value 2. So it doesn't do anything. But we could also have a slightly more difficult function. Let's consider f of x equals x squared plus 5. Then now if we try to do our x is 2, we obtain a f of 2 equals 2 squared plus 5, which equals 9, I think. So we can make a whole lot of complicated things with functions. But the nice thing about these functions is that you can draw them, you can graph them really easily. So for example, for our f of x, we could do 1, 2, 3, 1, 2, 3. We know that if we have x is 2, we get the value 2 back. So we could basically make a draw on the paper to a big plus sign and give it some numbers, give it 2 number lines, the number lines we had before, and at any value, at any x, this would be x, this would be fx. At any x, you're going to compute what the function is. So for example, at x equals 2, we compute that the function is 2. At x equals 3, we can find that the function is 3, because it gives the same number back. And so when you keep doing that for all values, you can kind of see a straight diagonal line in here. That's what really that's graphing. It's a useful skill. Okay, that brings us to the last point of the preliminaries, and then we can go get to the fun part. Numbers on their own aren't enough. For example, when we want to talk about temperature, we could give it the value 2 or the value 20, but that doesn't tell us enough. The value 20 doesn't give it a temperature. So instead, we need to add something to this number, and this is what is done with units. So for example, with temperature, we could be talking about Celsius or Kelvin. We need to give it some indication of what it is talking about. It needs to be related to a physical quantity. and a temperature of 20 degrees Celsius, this does make sense. And for example, a distance of 2 meters, this does also make sense. So in physics, we have a system of units that are, well, conventional. They're conventional units. We use these units when we describe quantities in our physics. And I hope I can copy this into... So for all the relevant... There we go. I suppose, where are you? Okay, that's a little bit annoying. But we have you. Almost there. There we go. These are all the relevant units that we need. So for time, I need my drawing pen again. For time, we are referring to this usually with seconds. For length, we use meters. For mass, we use kilograms. And we could also talk about current, for which we have the unit ampere. And temperature, we usually set to Kelvin. These units are kind of like the base of... I said someone is asking where mole and candela are. They didn't pay attention to the word relevant that I said. I'm stating all the relevant units. Anyways, these units are the conventional ones to use. With these units, we can make combinations. So, for example, when we will be talking about velocity, but velocity is, spoiler alert, distance over time. And what this means is our distance has units of meters, our time has units of seconds. So our velocity will have units of meters over seconds, meters divided by seconds. And there is someone is asking about Siemens. I'm pretty sure Siemens can be made with ampere and I think seconds. I'm not too sure on that, but it can be composed of these units, I think. Well, I'm sure. Okay, one last thing about units is, of course, we can, when we say something like, we have some tennis ball, why not, moving 200 meters, and we have another tennis ball actually moving 300, well, not 300, 3 kilometers. When we compare these two units, when we compare these two numbers, we should... Don't do that. When we compare these two numbers, we should not be comparing the 200 to the 300. We need to make sure they are both measured in meters. This makes sense, I think. And way to do that is to write the kilometers in terms of meters. Kilometers is 1,000 meters, so we would have 3,000 meters. And now you can compare these numbers together, because they both express things in the same unit. And then we see that the second tennis ball actually went a lot faster, and the person throwing them is basically a superhero. So, let's give one more example of that, where we compare the velocity of the first tennis ball. Let's just say we have the number 36 kilometers an hour, whereas the second one has a velocity of... Well, no, we just have a tennis ball going with this velocity, but we want to express it in meters per second, because that's our units that we use. And when we are talking to our physics friends, we want to give them a number that they will understand. We don't want to calculate the number they want to know. So the way to do this is, of course, you get the kilometer per hour, and you know that a kilometer is 1,000 meters, an hour is 60 minutes and 60 seconds in each minute, so 60 times 60, 3600 seconds. So a kilometer per hour is 1 over 3.6 meters per second. And now you can find this very arbitrary number. You can do 36 over 3.6. Oh, that's convenient. Which, of course, is 10 meters per second. So this is still kilometers an hour that we convert to, well, it's not entirely true. But anyways, you end up with a velocity of 10 meters per second. So units can be converted. That's main point here. And this is all about the preliminaries. So from now on, we are going to do actual physics. And in doing so, boom, boom, ta-da. Okay. Whoa. Let's... New whiteboard? I should not have clicked. It's fine. I'm sure it's fine. So, physics. What we have now is numbers, a way to describe physical quantities, units, and we are going to apply this to our real life world now. So I suppose a very nice example now, and also a title, would be the motion of an asteroid. But first, already mentioned, in physics we describe models, approximations to reality, and let's consider as a very simple model at first. The model we are going to describe is that of a one-dimensional line. What this means is, in easy words, is it's movement on a straight line. For example, we could have a car. That's the worst car I ever drew in my life. Anyways, the car could be moving on a straight road. This is an example of a straight line. As long as there's no curves, the car is going in one direction. We could also have a coin of the nice Tower of Pisa. It's a really lovely tower. When we drop it and we drop it straight down, it's a motion in one direction. We could have a ball rolling on the floor in one direction and no one is touching it. This is also an example of a one-dimensional motion. And lastly, we could have the asteroid that I already mentioned. And it's just an asteroid going in space. It's going to some direction. It doesn't change the direction. This is also why it is very important to consider models, because the moment, for example, the asteroid comes close to a star, there will be gravity happening, I suppose. And when gravity is happening, it's going to bend and it's not going to be a straight line anymore. So our model that we are using as a simplified version would not apply anymore, and we would need a different model. We would need to include gravity. But anyways, let's consider the asteroid. The asteroid is fun because I have a drawing of it. There we go. Let me erase all this. There we go. An asteroid. So we know our asteroid is going in a single line, in a single direction. It's not bending or curving. It's just going from one planet to another, sure. How are we going to describe this? The motion of how are we going to describe where it is, how it is moving, how fast it's moving, etc. All of these questions. For this, we are going to introduce numbers, of course. And in doing so, we are presenting ourselves with three choices we need to make. So first of all, let's add a number line. This is for position. Let's consider the position of the asteroid. We're going to give it some value. The first question we have is, where do we put the 0? This is a choice. We can make this choice. It's our way of describing it. So for now, we are going to put the asteroid or the 0 at the asteroid's position. The second choice we have to make, and it's already made on this number line, but the second choice we have to make is which direction is positive and which direction is negative. In this case, we are going to keep this direction positive because our number line is positive this way, but every minus sign could be a plus sign and every plus sign could be a minus sign, and we would get the exact opposite. Once again, this is kind of similar to how we define left and right. If you turn it out, it's different. It's a convention. It's how we want to describe it. So we can still choose freedom in which direction we want positive and which direction we want negative. One more thing is this determines its position. We have to choose where we put the 0, and we have to choose which direction is positive. But we also have time. For example, at some time the asteroid is here, but if we close our eyes, wait for some time, and then look back, the asteroid will be somewhere else. So once again, we need to make a decision where we put the time. And this is once again described by real numbers. So let me, you know what, let's get this as position. And for position, we use a variable x. And let's get a number line for time as well. And once again, we can decide where we put the 0. So we could let the asteroid start at time equals -2, or time equals 4, or whatever we want. For now, we'll just put it at 0. The only difference with position is, time is given by the letter T, but the only difference with position is that we let time run forward. Time is always evolving in one way, so we will just always take this to be positive. There is no backwards in time shenanigans, there's no tenet stuff happening, which is why we don't need to make the choice of which direction does time go, because we can't go back in the direction. Unlike the position, where if we have the asteroid moving forward, it could be turning around and move backwards. Totally legal. For time, this is not the case. So, all in all, we have 3 different choices we need to make. And I can summarize them right here. I think 1 is enough. As already said, we can choose the origin of the time. So where do we put the 0? We can choose where we put the origin of the position. Where do we put the 0? And we can choose which direction is positive and which direction is negative. These define a so-called reference frame. This is a word you see a lot in physics, which is why I want to highlight it, or a frame of reference. It's basically a perspective. It's basically saying we could be standing on the asteroid, and for us, we just define the time equals 0, position equals 0, that direction being positive, usually the direction of motion of the asteroid, and we're just, from our perspective, we see this. And someone else could be standing on this planet and could define a whole new coordinate system, and they could say, well, from our reference, from our frame of reference, from our perspective, we see this. And these could just be different numbers, but the moment we start comparing them, we should take a little bit care that they should correspond to the same things. There will be a very fun exercise on this. Okay, I think it's good to consider an example. Not because it's difficult, but because I need to keep up the image of clickbait. I have a beautiful drawing of a bee and flowers. Props to Zaki for this one. So, bee and flowers. This makes me happy. The bee is flying from flower 1 to flower 2. Let me get my marker back. Flower 1, flower 2. Also, props to Esteban for this, actually. He came up with the bee idea. Yeah, bee flying from flower 1 to flower 2. It's going in a straight line, which means we can use our model of motion in the one-dimensional line. We can use it on this bee. We are going to use that on this bee. But first, we need to define this reference frame. And to do so, we have to make the 3 choices. We first need to put the origin of the time. And I guess we could do that at the current position of the bee. We could then just give some numbers to the position of the bee. You know what? Let's not do it at the position of the current bee. Let's put the time equals 0 at when the bee was leaving the flower. So now it is at some later time, which we don't know yet. We haven't specified it yet. Go away. There we go. But we have made one of the choices. The second choice is the number line, and where we put the 0 of the number line. And we are also going to put that at the first flower. And then we need to choose which direction is positive, which it kind of feels intuitive to, of course, take this direction to be positive. These are not a skill. So that this direction, if the bee is flying from 1 to 2, its position is increasing. It feels more intuitive. Doesn't have to be, but it's nicest to explain. In particular, a nicer version of what I drew right here is given by U. No, that's the asteroid. I don't want U. U. There we go. This is one way of putting the reference frame. However, it's not the only way. We could also, which I was already attempting to do, we could also put it at the bee's current position. So let's get rid of all this. I love this tool. We could say this. Nope, we're still going to give this some arbitrary time and put the time equals 0 here. We don't touch that. But for the position, we could put x equals 0 here. And then we could choose our direction. For example, this could be 1, this could be 2. We choose to keep the direction the same. So this would be -1, and this would be -2. Totally legal. Instead of explaining it from the perspective of the flower now, we're explaining it from the perspective of the bee. And because I put a lot of work in this picture, I'm going to show this one as well. There we go. So in this case, we are describing it from the perspective of the bee. Once again, it's our choice of deciding from where we want to explain it. We could even explain it from the second flower. It's someone living on the second flower, like an ant or something, that sees a scary bee coming towards it. They could be giving their theory this way, or their description of motion of the bee this way, whereas the bee sees it as from the second perspective, and the first one, the flower, sees it on the first perspective. It just, once again, I'm emphasizing a lot on this, but it is a very subtle notion. It's very important to choose this reference frame and be consistent with it. Why? Because later we will be talking about, or actually in a second, we'll be talking about distances and such, and different positions. And once we have chosen such a frame of reference, we need to be consistent that this distance stays the same distance, because that's how we define it. And then we can be computing the difference between these two positions, how far they are away. And consistency is key in this case. Okay. That means we have done some progress. And in particular, we have yapped about space and time coordinates and about the reference frame. As a small summary, using some preliminaries, we are trying to describe an object using numbers to describe this position and the time. And to do so, we need to make three choices. These three choices, and this is referred to as a reference frame. All right, that's just the setup. Let's continue to some fun stuff now. And let's take this picture. This picture is nice. You. And we are hyping, so we are going to change the new color. Green. You know what? I don't like green. Purple or pink. There we go. So, right here, we have chosen a reference frame, and what we see is the B was at some time, which we're going to call T0. And the time it's at when it's at a later time, it's going to be a T1. These are, you can think of these as two measurements. We are just looking at the B where it is, and we are denoting, writing down where it is. This is at some time T0. This is at some time T1. The position of the B, we can also measure because we are looking at the B. And also, once again, we are giving an arbitrary unit to this so that we can keep our mathematics general, so that we don't need to change the same, choose the same reference frame every time, or put things 0, etc. So the first time we observe the B is at x equals 0, or x0, sorry, and the second time it's at x1. The first one is we took some time between measuring these two instances where we check the B, and this time is of course something you can watch on your stopwatch. You can just see how long it took you to measure again, and this is referred to as a time interval. And now I'm gonna hopefully do a cool thing. There we go. No, it's already. There we go. It's gonna be cool. Don't worry. So in particular, we can just calculate how long it took us, which is done. This is referred to as the time interval. This is meant to be a triangle. I knew this was gonna happen. It does not like triangles. Yes. There we go. I told you it's gonna be cool. Equation. The first equation is it's literally we compute how long we are measuring, or how long we measure again. No. Don't tell me. Okay. The second one is we can also measure how far the bee has traveled. And this, a new triangle, a new chance. This is by just computing how far it has traveled. So in particular, we are just checking the second position to the first position. We are measuring this distance between them. The second triangle was a success, I'm happy to announce. This is referred to as the time interval or the time difference. And this is referred to as the displacement. It's the difference between two positions. No, cancel. I just want to move you. Perfect. This delta symbol, this triangle, it's just an indication that we're talking about the difference. We are talking about how much something changed. It's common practice to use a delta for this. This is not scary mathematics, don't worry about it. So, perfect. Let's do this again. Another B? Or not another B? I would say another B. What even is that question? Almost there. Another B. So, once again, we are observing B. We are measuring twice, and we see that it has moved from the first position to the second position. The time it took was the time interval, the amount it traveled was the displacement. Okay, now of course what could happen is we could actually have a second B. Alright, 1 second. Do I have a picture? I don't think I have a picture, that's a shame. That's a shame. Anyways, for the next time. We could have a second B that also starts here. But actually, when we check this is t equals t0, they are both at the same position and both at the same time. They start at the same. They just continue. They just begin at the same point. And then the first one travels to here, but the second one travels all the way to here. Clearly, it's going much faster, as we would say. It did a lot more of traveling in the same amount of time. But we would like to quantify this. We want to give it some mathematical notion so that we can like compare this notion to other types, and then we can do stuff with that. And this is done. Let me get my math right. This is done by seeing how much it traveled, comparing it to how long it took to travel this. This is going to be horrible because I need two triangles. That's one. Who thought of using triangles for this? Yes. Okay. Anyways, we are going to see how much it traveled per time unit. So we are essentially just checking if we let it wait for, if we play it for 1 second, if we let it move for 1 second, how far does it travel? That's this quantity. And this is, of course, referred to as the velocity, or in this case, it's the average velocity. Because there should be a bar over here. It should be v bar, but I can't get the bar in the drawing. Average velocity. Very nice. If we want to write this one out, we would get v bar equals delta x divided by delta t, and a delta x, as we saw before, is just the difference between 2 points. So delta x is x1 minus x0, and delta t is t1 minus t0. So when we know when we measured, and when we measured again how long that took, the difference between that, and the position of the first time we measure and the position of the second time we measure, we can compute its average velocity. So we can now do this for both b's, and let's keep it simple. Let's say that we set t0 is 0. This is a choice we can make because we can define our reference frame. We also set this position to be 0. Once again, a choice we can make. And we measure for 1 second. Just to keep it simple. We close our eyes for 1 second, and we look again. Then we can measure where both b's are. So the first bee will be, let's say, at distance 2, at 2 meters. Whereas the second bee, it's Speedy Boy. It went for 4 meters. And so when we compute the average velocity of the first bee, I'm going to give it the subscript 1 for the first bee, it's going to be x1 is 2 meters, minus x0 is 0 meters, and we measured only 1 second later. So this is going to be 2 meters per second. And for the second bee, we can do the same thing, where now you only get a 4 here. So you get 4 meters per second. And you can compare these two numbers. You see that the second bee is twice as fast. And this is a mathematical way of explaining velocity, of the notion of how fast something is going. Note, however, that had we chosen our reference or our direction of position to be negative this way, so this would be 1, 2, 3, 4, etc., and this would be -1, -2, etc., then these positions would have gotten a minus sign, and now we're talking about minus velocity, minus average velocity. In this case, this minus sign here, what it tells you is that the object is moving in the different direction as the positive direction of your choice. So the bee is still moving this way despite the negative sign. It's just accounting for the fact that you chose this to be positive and the direction of the movement to be negative. So if you think about average velocity as a change in position, this is how fast position is changing, then every second it would go 2 more negative, and which means it would go still this way. Very, very nice. Okay. There is a funny consequence, however. Because what could happen is flower. Second flower, B. Let's actually put the B at the beginning. B. It starts to travel. We measure here. We see our B here. We then close our eyes. And we wait like 2 seconds or 5 seconds, whatever, however long. And then we look again. We make our second measurement. And we see the bee here again. It's as if the bee didn't move. We waited 5 seconds and the bee is here. The average velocity then is both these positions are going to be the same. So our displacement in position, or just our displacement, our change in position is going to be 0. It didn't move, which means our average velocity is also going to be 0 because it is dx divided by dt, and dx is 0. So we now have an average velocity of 0. but what could have happened in those 5 seconds that we were closing our eyes is the bee could have moved to the second flower and it could have moved back. That's legal. That could be. There's nothing that doesn't prevent it from happening. So in that sense, our observations, our average velocity, it doesn't contain all the information. Stuff could have happened. The bee could have moved. We can't know because we didn't take the other measurement in between. So had we done that, had we measured the bee first at the first flower, closed our eyes for 2.5 seconds, measured again, we would see the bee to be here. This is a bee and not a flower. And then we close our eyes, we look, wait 2.5 seconds, then we measure again. We see the bee back at the original flower. And now we get for both of these measurements, between the first measurement and the second measurement, we get some average velocity. We see that the bee has moved. And similarly for the between the second and the third measurements, we see that the bee has moved back, so it also has a velocity. And in this case, the velocity will be the negative of the other velocity, because they need to become 0 in the end. The only thing that changes is the dx becomes negative. Given that you measure halfway. So, key point here is average velocity doesn't contain all the information. And the way to get more information is to measure faster. We can push this notion. We can measure faster, measure even more faster, half it again, keep measuring. And at some point, what we can talk about is this is going to be a very it's not going to be very it's more of a motivation than an explanation. The mathematics will require a bit more, but what's going to happen is you can when you measure like instantly again, essentially, you can know the velocity of this bee at this point, at this moment in time. So if your bee is flying somewhere and you measure it and you measure it instantly again, calculate the average velocity between that, you can see you can talk about the velocity of the bee at that single point in time. And this is formally done with the theory of calculus. In funny notation, what you're going to do is move. You also move. What you're going to do is intuitively very simple. You're going to define the velocity of the bee at that single point as still your dx over dt, but you're going to make your dt really small. This is a funny limit notation. Essentially what this means is you measure instantly again. The time it takes to measure again is going to 0. So that's the instant I was referring to, with the asterisk that instant is not really defined. You need to take an infinitesimal and you get the notion of derivatives in that way. Doesn't really matter. For our purposes, just measure fast enough and you get the velocity of the bee at that single point in time. Easy. Okay, fun. Let's go back at our summary. There you are. So, where are we? We are talking about motion in one dimension, and we talked about space and time coordinates. We talked about the reference frame. We talked about the time interval and the displacements, which essentially tell you how much and how long the object took to travel. We talked about the average velocity, which is a notion of in 1 second how much does an object travel, and different objects with different velocities travel faster or slower. And we also covered the instantaneous velocity, which is just this velocity we defined by just measuring instantly again. So time interval, we got this, we got this, we got this, and we got this. Nice. So, time for a drink. 1 second. All right, let's see. Of course, when you're sitting in a car, you could be driving at some. Let me draw a car first. Window. It's got one of those racing car things. That was the worst car I've ever. That's even worse than the first car. Anyways, when we have a car driving at some highway, or when you're the one driving, or when you're the one sitting in the car, you could be driving at some velocity, let's say 50 kilometers an hour, or well, it's an exercise to the listener to convert this back in meters per second. But then you could hit the gas pedal, and at some later time, you end up with you're suddenly driving 80 kilometers an hour. And let's say this took like let's just say this took like it's a really fast car. It'd soon be 2 seconds. You went from 50 kilometers an hour to 80 kilometers an hour in 2 seconds. That's speedy. So now your velocity is changing, and in the same way that velocity tells you how fast the position is changing, it tells you how fast an object is moving through space. We can also define something for how fast the velocity is changing. And this is done with acceleration. Acceleration is the notion of how much your velocity changes. And in this case, we're going to first cover average acceleration. And average acceleration is denoted by a. And once again, the bar here, I don't think I explained this for velocity, but I'm putting a bar over velocity and over acceleration to indicate that this is an average. So this bar means we are picking 2 points, and between these 2 points we are computing the velocity. We don't know about anything that happened in between. Same for the average acceleration. This v, basically the instantaneous v, doesn't have. Don't delete that. Uh-oh. I can't get it back. Undo. Yes, it's back. This instantaneous v doesn't have this this average, because now we're not taking 2 distinct points. We're moving the points closer together. We are taking a small time interval as we can. So it's not an average anymore. Basically, nothing could have happened in between anymore. Very roughly said, the mathematicians will be angry at me. Anyways, not scary notation, very trivial notation. Move. There we go. We can, of course, find a mathematical equation for this average acceleration. If we define it as how much velocity changes over some time unit, how fast it's changing, then it's very straightforward to write the difference in velocity divided by the difference in time. In the same way that our velocity was the difference in position divided by the difference in time. And this quantity tells you how much velocity changes in 1 second. So for example, in this example, it went from 50 kilometers an hour to 80 kilometers an hour. So this would be position velocity 0. This would be position 1. So when we compute the average acceleration for this example, we have delta v divided by delta t. Remember that delta v and delta t, what they mean is onto button. That did not work. What they mean is the velocity. The delta is a difference. So the velocity of this first point minus the velocity of the first point, divided by the second time, divided by the initial time. So we essentially what we're doing is you check at some initial time. You make your first measurement, close your eyes, look again, make your second measurement, and we just check how much the velocity changed and check how much the time changed, how long it took us. And when we fill this in, we get our 80 kilometers an hour. That's our second velocity, minus the 50 kilometers an hour, divided by 2. I know I said seconds, but this is going to be 2 hours now. We were very slowly accelerating. It's just to make my units look nice. We can compute this, and what we find is 30 kilometers an hour divided by 2 hour equals 30 kilometers divided by an hour. I hate this. Equals, let's just say we have some magical number here. It is 30, yes, I know. But when we convert it, we get the very nice number of average acceleration is. Why did I do this? Forget the example. Let's say we have an average acceleration of 30 meters per second squared. Notice there's a square here now, because we are dividing velocity, which is meter per second, or a kilometer an hour, but you can convert that back, divided by seconds. So in other words, you get meters per second equals meter per second squared. Yeah, this is still divided by 2. I didn't finish the example. But yes, you should end up with. Oh yeah. Oh, I see. A good catch. This should be 15 kilometers an hour squared. Don't worry about that. It's all planned and coordinated. So, anyways, that's the first note. It has a square. It's a new combination of units. The second note is what this number means is that every single second, and let's make this 15 again. Every single second, the velocity at the initial point, which now we're doing everything at meters per second, after 1 second, it adds 15. So it increases by 15. Another second passes, it's now 80 meters per second. That is what average acceleration tells us. It tells us how much the velocity changes in a second, or in some time interval. Conceptually, it's intuitive. Mathematically, you just need to stare at equations sometimes. Okay. But we can do once again the trick of okay, let's say we have a car moving with this it's an alien car now, moving with this some certain velocity, let's say 10 meters per second, and then this is our first measurement. We close our eyes, make our second measurement, and we now see the car. It's at a later time, but it's still moving 10 meters per second. Of course, this doesn't tell us what happens in between. The car could have been accelerating to 20 meters per second and then deaccelerating back again. So we can again measure faster and faster how the velocity is changing. And with this, you can define the instantaneous acceleration, which is just measure fast enough, measure how much your velocity changes just really quickly, immediately. And this is, once again, with the funny limit notation. This is not scary. This is just a way of writing it down. You just check, you just send this time to 0, which means you measure instantly again. So that's velocity and acceleration for you, all constructed from numbers. It's very crazy how far we got, well, starting with numbers. Average acceleration and average acceleration. All right. Okay. Now, all constructed from bees and asteroids. That's right. We are doing great. You just need numbers, bees, and asteroids. That's that. So let's see, where can we go now? Yes. So what do we want to consider? Asteroid or bee? Wait, I have a question. No, I can't make a poll. That's not fun. All right, the first response will decide asteroids or bees. I got both.
I can make a poll for you if you want.
Yes, asteroid and bees.
Asteroid and bees.
Yeah, we'll keep the poll open for like 10 seconds, 15 seconds.
There we go.
Can I decide myself or... Wait, A and B, that's genius. This is Alice and Bob, but asteroids and bees. Does it close on its own, or do I need to click something to see it?
Well, I can close it, like...
But can I see the result or no?
I can tell you the result.
Yes, I think this is sufficient.
All right, I'm ending it done. There we are.
Bees! Excellent choice. What a fine gentleman we are. Okay. I'm sure we can clear this. Let's see. Where's my bee? There's my bee. Look at her go. Bee. So, you know what? Because I cleared the board, let's another quick summary. They essentially we have average velocity, delta x, delta t, and we can get velocity from this if we send delta t to 0. I love compact notation. Similarly, average acceleration, it's difference in velocity divided by difference in time, and we can get the instantaneous acceleration from this when we send time to 0 again. And both of these quantities, for average velocity, we would have to be talking about two measurements. But instantaneous velocity, we could talk about the velocity of this bee. And similarly, so it has some certain velocity at this point, instantaneous velocity. And similarly, we could talk about the instantaneous acceleration of this point, of the bee at this point, at this time. Actually, what could happen is if the acceleration and the direction of this arrow is corresponding to which direction of the number line you choose positive. So because I can, I'm going to introduce the number line again between the flowers, U and U. This is position now. Wait, I can. Why? I want you at 0. All right. So let's take positive to be this side, as the number line indicates. The velocity pointing this way, that means that the sign of the velocity is positive, which means that every second the bee's position is increasing, because the velocity tells you how much distance increases per time interval. So when this is positive, the bee just keeps going this direction. When the velocity is pointing in this way, what this means is that we drew the bee wrong, because the bee is actually moving in this direction. So when we measure at a later time, it's closer to this way. However, what could happen, actually, this is only the velocity arrow. For the acceleration arrow, this tells us how the velocity is changing. So in particular, when we point this towards the positive, that means that the acceleration, or that the velocity is increasing. So when we measure the b at a later time with this velocity, this means that our velocity is now a much bigger arrow, because it has a higher value. And this just keeps going. It's accelerating, it's speeding up. So this just keeps going. It gets faster and faster. But what could happen as well is that the b is moving in this direction, and the acceleration vector is moving right there. What this means, I said acceleration vector, what I mean acceleration arrow. So the sign of the acceleration, this was not an intended cliffhanger or spoiler for the next time. The intended direction, or the direction of the acceleration, is negative, which means that the velocity is now decreasing. So what that means is when we check the b at a later time, it has a smaller velocity. When we check it even at a later time, it has even smaller velocity. At some time, the b will be standing 0. It has no velocity. At a later time, the b is actually has a velocity towards the negative now. So it's moving backwards. And you can see what's happening here. When the velocity vector points towards the positive, acceleration towards the negative, the b is slowing down and it's reversing. It's doing a loop-de-loop. And then it just keeps going to the first flower. There will be some... There is an example on this, I believe. And there will be some exercise on this in the lecture notes, but I still have to write them. So stay tuned, I suppose. And to answer a question, I'm not teaching calculus this today. The goal of this lecture is to begin by the very, very basics. We started with simple numbers, like counting, with addition, and we are building up to basically the simplest model in physics. This first lecture it's very slow. I know this. Most of it is understood, which is good. But everything that comes after this will build upon this. So I don't want to take this as granted. We're just covering everything, and if it's redundant, then so be it. More for next time. All right, B, starting from the B6. Yes. So we can, if we make a measurement, our B is right here. If we make it some later measurement, our B could be right here. But regardless of whether we take or we make a measurement, this is classical mechanics, not quantum mechanics. And that means that the B is somewhere in between here. Disregarding of whatever moment we decide to measure, it's going to have an actual position. And in particular, what this means is it's a function of time. It's continuous. It depends. Our position depends on some time. So, for example, when we say that this is time 0, and this is also we define this as x is 0. This is where we define our frame of reference. Then this function of position evaluated at this time equals 0 will be 0, because that's where the B is at that point. This function is just telling us where the B is at a given time. At whatever time we insert, that's where the B is. So at some later time, let's say x t equals 1, this is t equals 1, we could ask this function, where is the B? And the B actually be at, say, x equals 2. So we get the number 2 back. Or, I suppose in meters, but let's ignore units for a second, which is a cardinal sin. Don't do that. It's just for ease of notation, I promise. But we could also ask about the value of about t equals a half, t equals 0.001. It should give us a value back somewhere in between here or whatever. What this means is a function, and a function we can plot. So we will get some type of a graph of how, that's not the graph I want, of how the B is moving in where it is at a certain time. That gives us already a lot of information, because if we know this function, we don't have to do our measurements anymore. We can just check, we can just read them. Now, of course, knowing a function, this function is true for the B, that's a whole other story. We don't talk about that. So for now, we'll just assume that we can describe the B with the function, and we'll just look at some certain functions and, well, see what they do. And this brings us kind of to the basics of reading graphs, getting information from graphs. There will be, and this is also in the making or in the planning, I suppose it's still in the early stages, but we want to make an interactive exercise on this, where on the website, shameless self-promotion, we can we present some certain page where the user can insert, play with some graphs, get information, or have to read information from these graphs. Based on this information, get to look at different graphs, etc., etc. So we will, for example, we could look at special points in graphs, like the how it's moving, if there is some peak or something. These will all have implications, and the idea is that you will play with it and understand it based on the guide that we give with the interactive exercise. But for now, let's continue a little bit further, because velocity, or rather the instantaneous velocity, and from now on when I mention velocity or acceleration, I always mean the instantaneous version. I never put a bar on there anymore. But they will also be functions of time, because we can talk about the velocity of the object at some certain point and at some certain time. And similarly for the acceleration. So what this means is we get some position graph, we get some velocity graph, and we get some acceleration graph. And of course, because the acceleration and why can I not remove this? Well, that's there forever. Because the acceleration and velocity are defined in terms of position and time, there will be connections between these graphs. They won't be independent. They won't just be some arbitrary lines. There will actually be some way of going between these graphs. And this is also going to be part of this interactive exercise. But let's see an example of this. So for example, let's say we do some magic and insert a pre-made graph in there. There we go. There we go. Now you draw. Okay, let's say we have an xt graph, and we these points here are measurements we took of the B. So we are going to go back to taking measurements. These are going to be 1, 2, 3, 4, 5, 6. That. This is a 0, 1, 2, 3, -1, -2. So in particular, the B starts at position -2, moves to position 1, moves back to position 0 in the next time step, etc., etc. We can look at, for example, this first time step between time equals 0 and time equals 1, where of course the difference in the time is 1 second, or just 1 for now. 1 second, fine. The difference in the position, we know that it's first at -2 and then it's at 1. So in total, this is the distance that has been traveled, which is 1, the final point, minus the initial point, -2. And minus minus is plus, so we get a distance of 3 meters. Which means that we can now compute the average velocity of this average velocity, dx divided by dt, which is 3 meters divided by 1 second equals 3 meters per second. What we can now do is we can do this for every single point. So we can also do this for 1 and 2. We can do this for 2 and 3, 3 and 4, and 4 and 5. Where is point number 5? We don't have a point number 5. Point number 5 doesn't exist. What we get is we get a couple different velocities. I'm going to use 2, 3 to indicate that between 2 and 3, 3 and 4, and V4 and 5. And so we get like 4 different values, and we can plot these values in a VT graph. And when we do that, we obtain the following graph. Let me copy this over. There we go. A VT graph. And now, still between like 0 and 1, our average velocity is 3, which means that we get a line here. Note also that we have one less data point because we are talking about the distance between, or the average velocity between 2 points. There's only 4 between 2 points, or consecutive points technically. So this tells us how we can go from this graph to from the xt graph to the vt graph. But there also exists a way of going back. And very, very briefly, I talk about this a lot in the lecture notes, and special thanks for Adrian for that, who wrote the main section. We can just start with the VT graph. And what we see is between the time 0 and time 1, it has an average velocity of 3 meters per second. So how much did it move is the next question we could ask. And well, this what we know is the average velocity is dx divided by dt. So what we could do is we could multiply with dt on both sides. And what we then get is dx equals the average velocity times dt, or technically it's delta t, sorry. This is entirely legal. We know this part, which is the 3 meters per second. We know how long it took, the ds, it's 1 second. So in particular, when we calculate how much it traveled in this 1 second, we get 3 meters per second times 1 second equals 3 meters. So now we know how much it has traveled. And when we look back at the original dx graph, we see that, yes, it traveled from -2 to 1. So yes, it did travel 3 meters. That's very nice, this consistency check. We can also do that for all the other ones, and we see that this pattern needs to hold. It needs to climb with 3, decrease by 1, climb with 3, decrease by 1, at least for these 4 points from these average velocities. And this gives us back the xt graph. With one small caveat. What we computed really was dx, which in particular is how much the object moved. And we found 3 meters. In 1 second, it moved 3 meters. But it didn't tell us from where it moved. It didn't tell us the -2. So only from the VT graph, we can only know, okay, something like this is happening. But we don't know where it started. For this, we need one more measurement of the b. We need to say like, okay, at time equals 0, the b is at that point. And then you could get all the information back. This, I guess, is a small thing for now, but this is going to be big when we go to calculus, not today. But essentially, defining this like initial point, or that it's also used referred to as like the initial conditions of the bee. It's needed in order to fully describe the motion of the bee. And funnily enough, we can well, actually, no, not. Let's wait with that 1 second. We can get a useful interpretation from this, where our v bar is exactly this height. So it's to this 3. So this is our v bar. Our delta t is exactly this this distance. So what we could do is we could like make this make an area out of this, and make an area out of this, and we know that the area of some rectangle is computed by the height, which apparently I don't know how to write height, times its width. That's like that should be a common way to calculate the area of a rectangle. So you just have the height. Height and the width, and to compute this area, you compute you calculate you multiply the height and the width. When we do that for this triangle, we find that our area is the height is v bar, average velocity, and we multiply with the delta t. And when we look at this equation, this is exactly our delta x. So from the graph itself, it seems like this area underneath here is exactly how much the b traveled. It moved. Don't do that. This is exactly how much the b traveled. We could do that for this distance as well, and we see that this is negative, and that's correct because it moved back. We could do that for this as well, if only I could draw straight lines. And similarly for this one. And so we find that we can compute the displacements by just calculating the areas under the velocity graph. And it turns out, by the theory of calculus, when you have a continuous function, so let's just say, don't have a continuous function x of t, or a v of t, sorry. And this is how your velocity moves with respect to time, then this area is corresponding exactly, no. This area corresponds exactly to how much the object moves, to the displacement of the object. So you could get the xt graph, except you don't know the initial point. So it could also be here, or it could be here. These are supposed to be the same shape. So once you know the initial conditions, so let's say it should be right here, then you know this graph is the right graph. And this is, it's a set calculus, more specifically it's integration. It turns out it's a very beautiful connection to physics, because what it means is we can now express our motion of our objects in terms of derivatives and integrations. We will not do this until next time. So for now, don't worry too much about it. Just the notion that, okay, if you have a velocity time graph, the area under your velocity is how much the object traveled. That's sufficient for now. That's just the rectangle, the area of this rectangle. Okay, so that's a short, well, maybe not that short. It's an overview of how to get information from a graph. And it turns out you can do exactly the same with acceleration, which will be left as an exercise, I suppose. You can find your acceleration in terms of from your velocity graph by like doing the same way we found our velocity graph from our position. And you can also return using counting the area underneath the accelerations. That's like free calculus right there. Okay, so let's go back to you. There we go. Motion in graphs. We're almost done. There is one thing left that I want to talk about, and I do kind of really want to talk about this before I end it. The stream, that is. And that's equations. So until now, we have done a lot of things pragmatically. We have basically conceptualized everything, talked about velocity and acceleration. We gave equations, but we didn't really do anything with equations other than plugging in some numbers. But with the algebraic manipulation I mentioned in the preliminaries, we can actually derive some things. We can derive new expressions, and this is also a very useful skill to have. In the lecture notes, this is represented or presented very, very clearly, so just read through that and you can get the entire, you can read through it a couple times to see all the steps we are taking. But for now, we can do some stuff. So for this section, we are going to assume constant acceleration. So in particular, the acceleration constant. The acceleration is just a number. We don't specify what number it is, but it doesn't change with time. And similarly, we usually denote initial position or like the measurements with t1, x1, v1, and t times 0, x0, and v0. But what we're going to do is we're going to define our reference frame so that this one is 0. This is allowed. We can also set this one to 0. We cannot set this one to 0 because we can only define choices for the time and position. The second time, so the b is somewhere here at first. The second time, or this is the initial time, so this is at t equals 0, x0 equals 0. It has some velocity, if you know. At the second time we measure, we're just going to call it t. We're going to keep it very general. It is sometime later we measure it. It's just a notation. We drop the subscript 1. Similarly for x, it's just going to be some position. And also for v, it has some velocity. We don't specify where we measure it. So it could be anywhere along this line where we measure it, any time. We just keep it as general as possible. And with this notation, what we can immediately conclude is that the time difference is t1 minus t0, which is t minus 0 is t. Our delta x displacement is x1, which is x, minus x0, which is 0, so we get x. And our delta v stays the same. Now, you're just stuck. Anyways, we can now define we can recall the definition for acceleration, the average acceleration, which is delta v divided by delta t, which we can now just fill in. V minus v naught divided by t. And we will now use our first manipulation. We're going to multiply both sides by t. So in particular, we end up with v minus v naught, this side, and then we get a times t. And in the next step, we are going to, this is times t, and now we're going to add v naught on both sides, and we get v equals v naught plus at. So in particular, what we have done is we have derived an expression for the velocity of the object at the second time we measure. So right here, we are finding this velocity, and the only thing we need to know is how fast it was moving initially, the constant acceleration, and at what time we measure. Nice equation. Secondly, can I delete? Secondly, we can find another equation, very useful, by considering. First of all, let's see an example. Let's consider the position, the 2 and 4 on the number line. When we compute the average of this, we know this is 3. It's precisely the point that's in the middle. But mathematically, to find the point that's in the middle, we add them together, and then we divide by 2. So this finds the value of both of them and halves it. And that's exactly the middle of the 2 points, the average. We can also do this with the velocity. So when we want to find the average velocity, we get the final velocity, which is in this case the 4, plus the initial velocity, which is the 2, and we divide it by 2. This step is allowed because our acceleration is constant, which means that our velocity, our acceleration doesn't change. So what's the best way of showing this? Essentially, the velocity could at most either go up linearly, like with a straight line, or go down with a straight line. That's the essence here, and we can find the halfway point of that of the 2 points on the line. If you don't agree, or if you don't, the explanation is not that helpful, then just take this as a fact for now, and just take it from this analogy. Just be careful that this does only apply for constant acceleration. What we can now do is we can also recall the definition of average velocity, delta x divided by delta t, which in this notation is x minus... Oh, I'm doing this thing again. All right. I'm going to change up one minor thing. I don't want it to start at x is 0. I want it to just be x naught to include more things. Move. So this would, the difference in x would still be x minus x naught. The reason why is it just explains, we can like later choose whatever x naught we want. You can just use 0 if you want to. That's optional. So in this case, it would be x minus x naught divided by t. And now, because this equation equals the average velocity and this equation equals the average velocity, they must be equal because they both are the average velocity. Which means when we combine them, we can just say f plus f naught divided by 2 is the same thing as x minus x naught divided by t, because they are both equal to average velocity. And now we can do some steps again. To find, we are going to multiply both sides by t. So we have v plus v naught divided by 2 times t, and this is going to equal x minus x naught. And now we are describing the position of the second time we measure the object, so this the second position of the bee here, where it is in terms of the time we measure and the velocities of both occasions. So in particular, we don't need the acceleration to describe this. If we don't know the acceleration, we could still determine the position using the other data. Okay. Doing some similar methods, you can find two more equations, which this is a reading exercise. They are fun, but in total you find these. Oh, that's sensitive. You find these four equations. Or I suppose I can also do this. Yes. Bigger. So you find these four equations. This is the one we derived, the first one. This is the one we derived where the x was still on the other. Wait, no, this is not the one we derived. This is the one we derived, and you can still find these two equations. Exercise. Essentially, all of these equations contain three of the objects, objects of interest, the quantities of interest, the x, v, a, and t. But every equation uses uses three of the four. So, for example, this one doesn't have position. This one doesn't have velocity, the v. This one doesn't have time. So if you don't know when you measure again, you can still find out all the relevant stuff. And this one doesn't use acceleration. So effectively, we have done nothing other than using definitions, equations we already knew, to get four, well, new equations, but they don't contain any new information because we didn't introduce anything other than definitions on things we already knew. But still, we have presented them in a very useful form. These can be used in different scenarios. When we don't know the time, we use that equation. When we don't know velocity, we use the other equation. So this is like the strength of algebraic manipulation. It's writing your equations in a very smart way so that for a specific example at hand, you can pick the right equation to use them. It's a very useful. Where is my whiteboard? Hello. Okay. Okay. Well, that's fine. Oh, it's back. It knows. So, like this skill of rewriting your equations is also a very important skill, and there will also be a exercise set to release to practice this skill. And moreover, constant acceleration is not chosen arbitrarily, not just to simplify things, because one very nice example is that if you have our lovely planet, the Earth, and you are close to the Earth, so you're like standing on top of it, which I would say is reasonably close to the Earth, and you drop a coin, then the acceleration of the coin that's falling downwards, because of the gravity, is constant. Close enough to the Earth, the acceleration because of gravity is constant. And this is the value most people have heard of. It's the g. It's the 9.81 meters per second. Or this could also be 0, depending on where you live. So it isn't actually constant, but it's approximately constant. So for a coin falling, you can use the four equations here to describe its motion, to describe how it's going, and even predict when it's going to hit the floor. And that's what makes physics so successful. It's using a very simple model. In this case, it's a one-dimensional model. It's the only thing we introduced is the notion of time, displacement, velocity, acceleration, and based on that, we can predict when something hits something else. Of course, once again, it's a model. We are ignoring stuff. For example, air friction. If we were to include this, we would have to make our model more difficult. But for a first occasion, a first meeting, well, I forgot the word for it. But if for a first time you're exposed to all of this, it's such a simple model describing something useful, something everyday life, a car going on the road, asteroid going towards Earth. Yeah, so essentially physics, I guess the main goal of this stream was to highlight everything you need for physics and build the necessary notions of motion that you need in physics. So velocity, acceleration. And using these notions, you can compute examples. I guess that's the best way of learning it. And talking about examples, in the library, I am pretty sure if you go to supplements or actually in the academy as well, is it? Okay, it's not yet in the academy, but it is scattered throughout the document as well. But there's also a separate exercise sheet where you can test your knowledge. Most exercises are going to be of this form. Props and high shout out to Adrian for helping write some of the problems. But this is kind of like the type of problems you can expect. Also, if you are taking a course in classical mechanics. So definitely you are encouraged to go have a look at them, go have a ponder on them, stare outside of the window when it's raining, and just think on how you would be able to solve that and then solve it. It's solving exercises is a satisfying feeling. I suppose that brings me to the end of everything I wanted to talk about. I yapped for way longer than I wanted to, 2 hours. But that's fine. You know what? For everyone who is still around, I have a bonus picture. You guys deserve it. Let me go grab it. You can see it already. It's my most awesome creation. It's the planet going towards Earth and another planet. There you go. Thanks for staying around. I hope to see you guys at the next one. So, paint. We did this, motion and equations, and that brings us to zoom out. Jack of all. Great. So, on, I don't think I can say menu, but as an overview of everything that we are still planning to do, I also made another poster, which, if you would be so kind to present yourself, that's not what I wanted to do. 1 second, let's see where it is. When I say I made the poster, I mean Make It Help Me made the poster, because the background is entirely due to Make It, and it looks good. Where are you? Schedule. Yeah, I think it's you. Yes, okay. So, everything that's upcoming that we're working very hard on this course. We want to make it a very educational course, and it is an essential part of the Slice of Pie Foundation. I would say myself, I might be biased, but as a small overview of what we're going to do is, first of all, we will upload a video on exactly what we have talked about today in specifically the model of the dimensional line. And we hope to have, there's some indications of the times. There is somewhere a disclaimer that they are all tentative. Okay, bye. But this is somewhere around where you can expect them. So there's going to be a video about this. There is also, which I didn't write down here, but there's also going to be the kind of like the stream itself, the lecture itself, in video form. There is going to be the exercise sheet that I just showed. It's going to be expanded upon. It's going to get a lot more exciting problems. And in line with exciting problems, I'm also going to do some exercise sheet on fundamental problems. And the idea of this exercise sheet is that I am using concepts that I use in my masters. For example, transformations and symmetries, and I'm going to apply them on this simple model. So even on this very simple model, you can get fundamental ideas in physics. You can get symmetries and Galilean transformations, all the things that are like very high right now in physics. You can get them in these exercises. Of course, they will be numbed down, simplified, but still, talking about time reversal in a model of one dimension, that's cool to me. There will be a video on reading the graphs, what I also did in the lecture today, but in much more depth. And alongside with that, there will be an interactive exercise sheet of this graph, so you can play with it, so you can try to understand it yourself with some guidance. There, somewhere in the next weekend, so in roughly a week, give or take a day, there will be another stream where we are going to do, it's basically a work hour, a question hour, or however you want to call it. We're just going to vibe, do some exercises, answer some questions. Everyone is welcome to propose some exercises, ask some questions about exercises. It's gonna be vibes. then to the exercises, I might upload solution sheets. Maybe. I will have to think about it. And lastly, I've mentioned it a lot in this lecture. There is going to be a stream on calculus, which effectively means that we are going to build calculus from scratch-ish and apply it to our physics. So basically, I'm making the claims that I used throughout the last part of the graph explaining. I'm going to make them proper, formal. And this is among other of the things that we have planned. So there is a lot more things that we have planned that I didn't include here because, to be frankly honest, I made this poster 20 minutes before the stream, 30 minutes before the stream. No time to do more. So with that, I suppose an exciting couple weeks, days, future awaits us. And everyone, I am very thankful for you being around here. Thank you.
That indeed. That in fact indeed. So yes, this has been the first of the many live streams of the Academy. Hope you've enjoyed. Do make sure to check out all the resources available. Once again, I am going to link the page to the Academy where you can find them organized, but they also exist in the library in case you'd like to check it out. Everything is powered by the library, and as the upcoming days are slowly rolling out, we will be actually introducing even more things. The Academy is only just beginning, and the more will be needed, the more we will do. The more we will do, the more will be available, and we hope that you will enjoy it. I suppose that will be it.
But 1 second. I have one last comment to make. If someone is reading through, when someone is reading through the lecture notes and they find themselves with either questions, suggestions, improvements, rephrasement, anything that could improve the form, the teaching, the understanding, I encourage you to reach out to me because I am still looking for a couple of proofreaders to ensure that everything is not only factual, which in this case it's still not too difficult, so the factual part I'm not worried about, but mostly written in a very understanding way, which is a very, I would say, difficult skill that I am experiencing. Not that I don't have, I mean, it's difficult to make everything clear. So if you have any suggestions, please reach out to me. Every help is appreciated with that. Yes. Word back to you.
Right, and as one last thing, in the Discord server we have channels dedicated to the Academy because I wanted to have a place where discourse about the Academy may take place, so go there if you'd like more questions. And that'll be it. I don't like talking about things in hypotheticals. I don't like saying things that we will do, we might do. I'd rather just do them and show them to you, so once they happen, then you'll know. And for now, I suppose that'll be it.
Thank you
Thank you all so much for watching.